Welcome to Horn Online Training, Training Module 13.2, Solid Carbide Selection. I'm your trainer, Edwin Tunney, Training and Technical Specialist for Horn USA Incorporated. If you've attended any of our training on solid carbide, you've probably seen this slide before, but this is a basic breakdown of all the different solid carbide systems from Horn. So you can see that we have a big variety of Endmills, and the purpose in this training today is to sort of help you decide what direction you need to go when selecting an Endmill. So we have four main systems of solid carbide tools and solid carbide, but also modular system with the DG. So you have the DP series of Endmills, that's for regular steel. You have the DS high performance Endmill series. You have the DC Endmill series. The DC is more or less the little brother of the mini milling system. You have access to groove milling, threading, and chamfering. So what's interesting about the DC too is you get down to really small thread profiles. If you look at the DS line, it's broken down even further, and more or less it's basically on a materials type basis or a process type basis. So you have high strength steel, you have aluminum, you have titanium, you have cobalt chrome, and then you have trochoidal or high dynamic cutting as a process. And then you also have CVD-D. That's a tipped diamond tools for machining non-ferrous alloys, as well as select sintered carbide machining. To look at the purpose of all these tools, the DP's purpose is it's really a series of performance Endmills, but it spans a broad range of materials and operations. So if you're not familiar with the ISO system, you have P is steel, M is stainless, K is iron, N is non-ferrous, and S is heat-resistant alloys like titanium or nickel. So the DP covers a broad range of materials, and you use this for competitive performance, but at a lower cost. The DS line of Endmills, as mentioned, those span several different material categories, but they're separated by those categories. So there's not really general purpose Endmills or performance Endmills, but they're not general purpose type Endmills. They're high performance. So it's a high performance line for steels, stainless, iron, non-ferrous, heat resistant alloys, as well as hard materials. So you use the DS line when you have a difficult application and you need to maximize the performance of the tool. The DC, so the DC is a complementary system to the mini milling, but for smaller bore diameters. You have groove milling, thread milling, and chamfering. When to use this, the DC series, you can apply that when milling in small bores and cavities. The DG is a modular system, so it's a screw-on modular head. It's solid carbide with a brazed steel interface, and then you'll have a steel front end and then a carbide back end. So a very good tool from a modular perspective. You're going to use those for long reach applications when solid tools are not cost effective. A little bit about the nomenclature. You'll notice in the newer catalogs, the nomenclature has changed slightly, but it's very easy to follow. So you have the first 4 characters of the nomenclature are basically describing what line the tool is in, and then the features. So this would be in the DS line, multi-flute with a radius, so with a corner radii. So those are fairly easy to follow. The next is the number of flutes. The next is the cutting diameter in millimeter. And just to note, all of the horn solid carbide tools, they are a metric line of both the DP as well as the DS and the DC and the DG. These are all metric lines. But as always, we make a lot of specials. So that's a discussion you can have with your horn application and sales engineer or manufacturing rep on quantities, if it makes sense to have an inch tool. The next comment is the radius. So that's the corner rad. Then you have a length and diameter multiplier. So this is a 3 times D on the flute length. So fairly easy to follow. All of these products can be found in our new solid carbide mills 2020-2021 catalog. So getting into the various individual end mills within the systems. So within the DP, you have several different end mill selections. You have the DPX, which is for roughing and finishing, the rougher and ripper profile, the DPS, the DPSB, so that's roughing with chip breakers. You have the DPSV, which is roughing plane, unequally twisted, which means it's variable helix. You also have roughing with a corner chamfer. You have torus end mills. You have multi-fluted end mills, ball nose, as well as deburring tools in various included angles. The DS system for high strength materials, less than 50 Rockwell. You have the DSK, the Trochoidal DSFT, the DSH, which is a double radius, so more or less a high feed tool. Torus end mills, multi-flute sharp, multi-flute with corner radii, roughing corner radius, roughing chamfer, chamfering 90 degrees. You also, within the DS line, you have micro tools. So we go down very small in diameter, smallest diameter of 0.1 millimeters in the DSKM ball nose, as well as the micro torus end mills. Very good shank tolerance, corner radii, really from 0.1 to 1 millimeter, starting at 0.5 millimeter. Multiple reach lengths, and the grade is TS3K, which is titanium aluminum nitride coating. DS for hard materials. So if you have a heat treated component and you need to machine that, the DS has a line for that. You have DSKH, which is your ball nose. You have a torus end mill. You have multi-flute sharp end mill. You have a multi-flute with corner radii. And you also have a micro ball nose and torus as well to fill out that program. In addition to higher strength alloys, heat treated alloys, we also cover cobalt alloys. So your cobalt alloys like ASTM, F75 that you would find in a medical application. You find cobalt also in aerospace as well for heat resistant parts. So we have a ball nose for that. That's a DSKC. You also, a lot of 5-axis work in that sort of market segment. So you have a DSKC with a 220. So you can go over the tangent point here and use this in 5-axis applications. You have Cobalt alloys, Taurus Endmills for Cobalt alloys. You also have multi-flutes as well for Cobalt-based alloys. You also have a line of DS Endmills for aluminum, from micro ball nose to Taurus Endmills with radii. Single flute tool is a very good tool because you can do plunge in to the material and rough out a pocket. It's kind of a good end mill to have around the shop. You have ball nose multi-flute tools, finishing sharp. So this is an end mill with extremely highly polished internal flutes for good chip evacuation. You also have roughing end mills with a corner chamfer in the DS FA, and as well as a DS FRA, which has a ripper type profile to reduce forces and break the chips up. Both of these systems, the DS FA, the DS FRA, both of those have internal coolant, which comes out the end of the tool, not on the internal part of the flute, but comes out the end. You also have a DS line for titanium, specifically for titanium. You have the DSRV.4 and the DSRV.5, which means 4-flute and 5-flute. These are specifically designed to machine titanium, highly polished flute, very, very good run out tolerance, 2/10 on run out on the tool. You can get these in different lengths as well, 2 and 3 times D, and titanium aluminum nitride and titanium silicon nitride coating on these for a very good tool life and wear resistance in titanium. You also have a DS line for trochoidal milling. So if you're not familiar, trochoidal milling is the basic concept of just taking little bites out of the material, reducing the cross section of the chip to a very, very small area, and not wrapping the tool, but just taking little bites out of the tool. And that's also a highly polished flute and very, very accurate run out. This additionally comes in a 4 times D option as well, since a lot of the productivity in trochoidal milling comes from taking very deep depth of cut with a very shallow AE or width of cut. So we have all this great product, and the problem is when you have a lot of a product is how to decide what to use and where. So hopefully we'll help with that. So as far as the DP system, the DP system is a little bit trickier to understand what to use. The DS is designed by materials. So if you have hard material, you use the DS Endmills for hard material. If you have titanium, you use the DS line for titanium, and that's going to give you the best result. But the DP system is a little more difficult to understand. So that's what this chart is for. So you see for roughing, you'll use the DPS Endmills, the DPSB, or the DPSG. And those are in various helix angles, which we'll talk about the effect of that in a future training. But for now, just understand if you're roughing, you want to use either the DPS, the DPSB, or the DPSG. So the DPSG, the feature you can see, it does have a corner chamfer, but these are typically you use them in a 3-flute configuration to rough out a pocket. when you're talking about semi-finishing, so either you're doing a roughing op, but a lot of it's doing semi-finishing where you're not really taking over 50% of the diameter of the tool, you're going to want to switch to the DPX tool or the DPSV. So the DPX tool is the difference between the DPX and the DPSV is that you have a radius on the DPX and you have a corner chamfer on the DPSV. So both have 35 to 38 variable helix, and both cover sort of the same range of applications as just one with a chamfer and one with a rad. The DPTR is a torus end mill, so there's additional clearance in the center so that you can do sort of profile milling, which is what you see here, that you can do with a torus. So shallow profiles like you would find maybe on a knee joint or a medical part. Finishing side, finishing usually you want to pack as many flutes as possible. So you'll find the DPM end mill, that's 45 degrees, and you're not going to do full slotting with this tool. You're going to do either trochoidal milling or you're going to do high speed milling to accomplish a pocket or to bring a part to size. As you can see with the DP tools, very, very good run out on the tool, and they cover a range of materials. So these are going to be your more, I wouldn't say they're high performance end mills, but they're going to cover a broad range of applications. They have a front end tolerance of H9 and a run out tolerance of 10 micron. Lastly, you can see the DPK on DPFF. So those are chamfering tools. Those are fairly self-explanatory where you would use those when you need to do contouring, profiling of a part, or you need to produce a chamfer. So there is a logic to how you pick an end mill. There's a few features that you need to look at from the component perspective, constraints that you need to reach, and then you look at the productivity side. So you can kind of think of this in two ways. You have the dimensional constraints that you must meet, and then you have the productivity constraints that you need to meet or exceed. So for dimensional, you have obviously the diameter. So you need to drive a radii really anytime you're going into a corner. So you need a small enough tool. Your diameter needs to be smaller, or the radius of your tool needs to be smaller than the radius, smallest radius of your part. You also have the L2, so you need to reach whatever feature in the part. So you have your length, or your flute length has to be met. And then you also have a corner radius. So especially if you're doing finishing, you need to really consider that your corner radius needs to match up in the corner. Or if you're roughing, you can get by. A lot of horn tools have a 45-degree chamfer, which is excellent if you're doing a roughing application. And then you come back and do your finish with the corrected radius. But those are the dimensional constraints that you need to meet for the part. Now, where you have more flexibility is in your productivity side. So your productivity side is how you select it is based on the material. You don't want to use an end mill design for aluminum in a piece of heat treated steel. And likewise, you don't want to use an end mill made for heat treated steel in an aluminum application. Just the edge geometry doesn't match up, and you won't be successful. The other thing is number of flutes, and then MRR. So those are the constraints that you need to deal with. Number of flutes, how that ties in is if you have a very sticky material that produces a bigger chip, then you don't want to pack a bunch of flutes on the tool or select a tool with a lot of flutes if you plan on doing semi-finishing to roughing with it, because it will just clog. And then your MRR, you have to think about that, you know, put pencil to paper and figure out what your MRR needs to be and whether that tool can meet that. I show this just as a side. This is a formula I learned a long time ago. I think it was a Boeing company or whatever uses this formula to sort of analyze a tool and its value to the process. So the first thing to talk about is the cost per cubic inch. So if you figure out the cost per cubic inch, you can compare several different options, from putting more flutes on a tool to using a higher value for roughing on a tool. So if we break this down, MRR is material removal rate, and that's made up of the width of cut times the depth of cut times the feed. So that's your MRR. And then that's given in various units, but commonly in inch units, it's cubic inches per minute. In metric, you'll commonly see cubic centimeters per minute. So in the formula here, the AE is the radial width, the AP is the depth of cut, the F is your linear feed rate in inches per minute. And the other part of this formula is all your cost. So your labor rate, your machine rate, how long it takes you to change a tool, and so forth. So if you look here, you can simply, the end result is you're gonna have cost per cubic inch. So on the bottom here, you put the cubic inches. On the top, you put the tool cost divided by the tool life, plus the machine hourly rate divided by 60. So you're essentially putting it into terms of minutes. And then your labor rate, your hourly labor rate, and you divide that by 60. So you're putting it in minutes. So you're just putting all the terms in terms of minutes. And then you have your tool cost, or your tool change time divided by your tool life in minutes. So boil that down and you end up with a very good assessment of a tool. So if you have a lot of tool change time, but you have a high MRR, so the tool can rough out a lot of material very quickly, then your cost per cubic inch comes down. And likewise, if you have a light MRR, but the top half here, you're not investing a lot of time changing out tools, you also have a good cost per cubic inch. So I think it's a good way to sort of compare and calculate the financial efficiency of a tooling system. You also have a situation, so the last formula was for roughing. So this formula is for finishing. Since finishing typically only takes one pass. If you're running titanium or nickel alloys, maybe you take a spring pass, but typically finishing is a one pass type option. So if you're comparing finishing Endmills, then you need to use the finishing formula. And so when you're talking about a cost per square inch, you talk the MRR in terms of the depth of cut times your feed rate. So you have your removal rate now is in square inches per minute. Same radial width of cut as your AE, your AP is your depth of cut, and your feed is your linear feed rate in inches per minute. You plug and chug the same exact formula. The only difference is you on the bottom here, you have a MRR in cubic inches or in square inches. So cost per square inch. So I think it's a good way to both evaluate both cases, either for roughing or semi-finishing, where you're taking multiple passes, or in a case for finishing, where you're just taking one pass. So you can compare. And most of the time in finishing, you're looking at the tool life and the number of flutes. So the productivity is generally coming from the cutting speed you can take and the number of flutes. So what are some other ways that you select a tool? So material and the hardness is the first thing. Really, that's the first thing to look at. Is it a hard material, soft? Is it ductile? Is it abrasive? Is it reactive? There's also a new ISO that you don't see very often, but is O, so that's other. So that's anything that doesn't fit in the first categories of ISO material classification is other. So the reason I mention that is the CVD-D Endmills, which machine non-ferrous alloys, but specifically tungsten or sintered carbide. So sintered carbide can be machined with the CVD-D. You also look at the geometry, diameter required. I typically, you really want to use something much smaller than your radii to get the best use out of the tool. But you always have to balance that with the the length in cut as well. You also want to look at what corner radii are available for that system. Your wall to floor thickness, is it a very thin part? Do you need to use a sharper tool to manage the forces that you're imparting on the component? You also have processes, so high-speed machining, trochoidal. Are you full slotting, helical ramping, deburring, finishing, roughing? Is the component rigid? What that has an influence on the tool that you would pick. Machine limitations of the machine, the rigidity and the feed rate, productivity, the MRR, the tool life, the surface finish requirements, the dimensional requirements. Not all tools, obviously. If you look at some of the sinusoidal end mills, they're not designed to give you a good surface finish. So take that into consideration. You also want to think about, you employ tools that fit the bill. The DC is a perfect example of that. So you have the DCR, which is for full radius groove milling. The DCN is groove milling. The DCX is a little bit bigger T-max or TIFA into the part, depth of groove. The DCF is a chamfer milling tool, and the DCG is for internal thread milling, so down to M1 by 0.75, so very small thread profiles can be machined with the DCG. The DG tool, as mentioned in the beginning, the main sort of purpose in the DG is when you need to reach into a part and a solid carbide tool is not practical. So the DG system from Horn is not a steel shank. It has an interface, a steel interface, but the shank of the tool can be purchased in carbide. So you're getting the stiffness of carbide without the huge expense of a very long carbide tool. So you have the ball nose tools, you have multi-flute, you have roughers with chamfers and radius, you have a ripper profile, you have chamfering, you have a high feed tool. So this is a good option to clean out corners. You have a corner rounding tool with the DGV. You also have conical ball nose like the DGVZ. So these are used a lot in a big gear production. You can get into the gear tooth with that on a 5-axis machine. On the holder side of things, you can see you do have a steel option. You have a 90-degree non-shrink fit steel. So if you've ever put a steel holder in a shrink fit, it doesn't ever come out again. So that's why they note that non-shrink fit. But then you also have a carbide shank. So you have carbide, steel, and then a carbide bit on the end, insertable, exchangeable tool in 90 degrees, 89 degrees, and 87 degrees. So different shank configurations to reach out with that tool. You also, the DS line, as mentioned, this is for non-ferrous alloys. This is a CVD-D diamond tipped. So CVD-D is a very high purity diamond because it's just like the CVD-D process you use for coating, but you're depositing diamond in different thicknesses. That's what the different grades are. HDO3 is 300 micron, HDO5 is 500 micron thick, and HDO8 is 800 micron thick. And you can find these in different configurations and down to really small diameters. So for a ball nose, for example, you get down to 0.2 millimeter diameter. Also micro torus from 1 millimeter, and then torus Endmills, and then multi-flute Endmills. So these are all designed more or less for, you can see from their design, for finishing. So they're designed for finishing. And they can also machine sintered carbide. So that's a pretty unique feature of a tool. So if you want to touch up a die set, a carbide die, you can employ some of these tools to make that happen. Thanks for joining us today. Don't forget to hit the subscribe button so you get alerts when we add new training videos. Thanks and have a great day.